This is Radio TV Phono Nut, and what we have is an RCA Victor portable 3-speed record player from probably the mid to late 50s, and it's sick. It doesn't work. I'm getting absolutely no hum or no kind of amplifier action, so let's open this up and troubleshoot it. Okay, we have it torn apart, and as you can see, this is just a typical single tube amplifier, which most of these little record players from the 50s and 60s had. And right off the bat we see a resistor that is cremated. It looks nice and toasty. It's coming off of the B+ output of the selenium rectifier, and the other end is connected to the first section of the filter capacitor can here. Now I could just go ahead and replace this resistor and turn it on, but there's a 99.9% chance that the new one would just go up in smoke too, because one of the rules of electronics is that resistors generally just don't cremate themselves on their own. When a resistor is fried, something made it fry. And before we slap a new resistor in there, my job is going to be to try and determine what made it fry. Did the selenium rectifier short and put AC through the resistor? Did the electrolytic filter capacitor short? Did one of these other capacitors short in the B+ line? What happened? Okay, the first thing I want to do is check the output of this selenium rectifier. If it's good, I should get DC out of it. If it's shorted, I should get AC out of it. We don't want AC. So this, of course, is our incoming AC. We have our meter connected to circuit ground. I have it set to DC volts, and we'll check right here and see what we get. So let's turn on the juice. And yeah, that motor is making a loud scraping sound. And I'm getting 1.8 volts DC out of it. So let's flip our meter to the AC scale and see what we get. And I'm betting this selenium rectifier is history. Yep, the selenium rectifier is shorted. We're getting AC voltage coming out of it. So that's what. Now what happened was, selenium rectifier shorted, sending AC to our first filter capacitor, or our first section of the filter capacitor, and since the capacitor blocks DC and passes AC, since we fed it with AC, it shot that AC right to ground, which effectively placed a short across this output here, and this resistor just couldn't take it, so it cremated itself. So what we'll want to do is replace this selenium rectifier with a silicon diode. Now one would think that you could test this selenium rectifier for a short on the lowest scale of your multimeter. Well, as you can see, I'm on the 200 ohm scale and I'm not reading anything. Move it up to the 2 megohm range and see what we get. Yeah, 388,000 ohms. Let's reverse our polarity and see what we get that way. 780K that way, which, if it was good, you should only get a reading one way, but the best way to test one is like what I did first. Have this output resistor disconnected and check your voltage coming off of it. If it's good, you'll get DC. If it's bad, you'll get AC coming off of it. And this one's bad because we're getting AC that's pretty close to the 120 volts AC line voltage coming out of this selenium. So if we look at this rectifier, it's nice and shiny and looks new, but that doesn't mean anything. And for those who say these never go bad or rarely ever go bad, well, here's one that went bad. And I will say that in all my years of working on stuff, I've only seen a handful of these go bad, but they can fail. However, the silicon diode that I'm about to replace this with is much more prone to shorting out, especially if a power surge or lightning hits the item. One thing I can say about these old seleniums, the internal resistance provided sort of a built-in surge protection, which is something you don't get with a silicon diode. Over the years, I've repaired countless televisions and other pieces of consumer electronics that had shorted silicon diodes due to power surges and lightning strikes. In fact, I remember this one older guy had a Zenith 25-inch console TV from about 83 or 4, and this would have been back in the mid-90s. I probably fixed that set 3 or 4 times for him. Every time lightning would strike close by his house, it would pop 1 or 2 of the rectifier diodes, and when that happened, I'd just go ahead and replace all 4 in the bridge rectifier network, because there's been times that I've replaced the 1 or 2 bad ones, and then the 1 or 2 that remained would short out, so it's just best to go ahead and replace all of them. So what I'm going to do here is mount a terminal strip to the chassis, and we'll install a 1N4007 diode. Have no idea what value this surge current limiting resistor was. It was coming off of the original selenium rectifier, and I really don't care, because since the silicon diode is more efficient than this selenium rectifier anyway, the B+ voltage will be higher, which means this resistor will need to be higher to keep the B+ voltage somewhere in line with what it's supposed to be. And I'd say around 120 volts would be a good value for B+ voltage, so we'll just install the 1N4007 and try various surge resistors until we find one that gives us a B+ voltage that I'm happy with. That's the easiest way to do it without all of the mathematical calculations. The resistor will probably be somewhere between 33 and 68 ohms, somewhere in that value. Okay. Soldered in a new silicon diode on a terminal strip that I soldered to the chassis. AC comes in here. Output of the diode, which is your banded end, goes into this 47 ohm resistor, and the output of this 47 ohm resistor will go to the first section of the filter capacitor. I just went ahead with a 47 ohm. I didn't bother to test anything. Like I said, the voltage is not that critical, and I've used that value before. Now, before I connect between here and our filter capacitor, I want to take a ohm meter measurement and make sure there's no short on the B+ line to ground here, because if something indeed shorted there, it could have very well been what drew too much current through the power supply and cremated the selenium rectifier and the resistor here. So let's see what we have here. Alright, there's our filter capacitor, and on the meter I'm reading 3 ohms. I'd say that's a dead short any day of the week, and we need to find out what is shorted here. Is it this filter capacitor, or is it something tied to it? Okay, here's what we have tied to the filter capacitor. Our audio output transformer primary connects here. We have a resistor that connects here that goes between the first section of the filter capacitor and the second section of the filter capacitor. And then we have this capacitor here. One end of it connects to our filter capacitor, and the other end goes back here to the tone control. Okay, I'm looking mainly at this filter capacitor, although this paper capacitor could be shorted depending on how this tone control is wired up. Let's see if we get what we get here. Okay, we get no reading to ground there, so that pretty much rules out this capacitor being shorted. Now, that narrows it down to, could this resistor back here be shorted? I've never seen it happen, but anything's possible. Let's check it. And I'll simply do that by moving our ohm meter lead over to the other end of the resistor. Okay, I'm getting a short on both sides of this resistor here, but it doesn't make sense that resistor would be shorted and cause this problem, so I'm looking more and more at both sections of this filter capacitor being shorted. Okay, I've completely disconnected both sections of the filter capacitor, and not only is section number 1 shorted, section number 2 is also. Here's section number 1 reading a low resistance. It can't make up its mind what it wants to read, but it's reading way too low. And here is section number 2. $11 ohms, 10 ohms. So yep, that needs to go. And there are no other shorts on the other B plus lines, and there's really nothing to this. You got B plus going through the output transformer to the tube plate, and then off the second section you have B plus going to the screen grid of the output tube, and there's no shorts noted there. So we just need to go ahead and replace this filter capacitor. And I know some of you are probably saying, why is he wasting all this time teaching us how to diagnose circuits? If he had just replaced every part on the chassis, then it would have worked. Well, that might have worked, but I run into a lot of sets, radios and phonographs and whatnot, where people were very good at swapping parts, as in capacitors. You know, a lot of people on the internet act like that capacitors are the be-all, end-all to vintage electronic repair. You know, replace all the capacitors and the equipment will magically start working again. Well, I agree that old paper capacitors like this need to be replaced, but more times than not, simply doing that is not going to make your equipment magically function again. And when that happens, you need to know some basic troubleshooting skills, or else you'll be one of those that does a nice job or a not so nice job at replacing all of the capacitors, and then when the equipment doesn't work, then you'll be clueless, and the thing will sit up on the shelf for 5 years until your wife or whoever decides to clean out one day, and your stuff will go to Goodwill. So, you know, you really need to learn how to troubleshoot this stuff. Okay, we have everything redone. This is our chassis isolation capacitor here. I'll replace that with a safety capacitor. This is our tone capacitor, which is a 0.1, and this is our cartridge coupling capacitor that couples the cartridge to the volume control, which is a 0.01. And I attached our filter capacitors to this terminal strip, and I had to use some longer wires here to run our newly installed filter capacitors over here to our tube socket. Our 150 ohm cathode bias resistor was up, so I replaced that. This resistor here, which is a 10k ohm that's in our power supply, it's still within tolerance, so I left it. So I think we're about ready to fire it up and see what happens. But first, let's check from our B plus lines and make sure there's no short. That looks good. And now let's move over here, right there. And that looks good. And this input filter is a 68 microfarad, 250 volt. And the second filter is a 47 microfarad, 250 volt. And there are, 200 volt. The original one was 150, but I decided to go with 200 and 250 since we have solid state rectification that will produce high B plus until the tube warms up and starts conducting. And another possibility I didn't mention, the selenium rectifier could have shorted, and when it dumped AC on this capacitor, it could have taken it out. Or like what I said before, the capacitor could have shorted and taken this stuff out, but it really doesn't matter. All the parts were bad and we replaced them. Okay, let's fire it up, see what happens. Well, we have activity, and would you believe this old crystal cartridge still has output? Yeah, that cartridge has got plenty of output, but the needle is shot. And I probably am going to have to up the value of that 47 ohm resistor. I'm getting 150 volts going into the audio output transformer and about 110 on the screen grid. And that is a tad bit high, so we'll probably up that resistor a little bit and see if we can get it down a little lower. And here we are with a 78 needle. It's got plenty of volume. Okay, I'll replace the 47 ohm resistor with a 100 ohm resistor. That brought the B plus down to about 135 volts, which is a little better. And I need to order a couple of fresh needles for this cartridge and clean and lubricate the drive mechanism, which I'm not going to bother with in this video because you've seen me do it a million times and it's the same procedure as it was last time. But yeah, we have it working pretty good now.
It happened at the Festival of Roses, and every year the story is retold. As I hear the zipper play.
Alright, there you go. I hope you got something out of all this. And thanks for watching, and more to come later.